Tonight, we are going to dive into the story of the most colossal star humanity has ever found. A star so impossibly enormous that if you could lift it out of its corner of the galaxy and drop it where our own sun currently rests, its blazing surface would push outward past the orbit of Saturn. Mercury, Venus, Earth, Mars, even the king-sized Jupiter, all of them would be swallowed whole, sitting buried inside the outer skin of this star's atmosphere. By the time we reach the end of this video, you are going to understand exactly how astronomers stumbled upon a star that is barely managing to hold itself together against its own searing radiation, why it sits perched right at the very brink of what physics and nature will permit, and how its existence rewrote what scientists believed about the absolute upper boundary of stellar size. Before we begin, if you find yourself drawn into the mysteries of deep space the way we do here, take a moment to like the video or subscribe. It costs you nothing, but it genuinely helps us bring more of these cosmic explorations to people who share that same curiosity. Now let us begin. The year was 1990. An astronomer named Charles Bruce Stephenson was carrying out a methodical, systematic sweep of the heavens, hunting for clusters of massive stars buried in the dust-clogged corners of our galaxy. His attention had turned toward the constellation Scuti, a small and rather dim grouping of stars in the southern hemisphere of the sky that lies directly across the bright plain of the Milky Way. This stretch of sky is overflowing with stars, gas, and thick veils of dust. It is one of those regions where our home galaxy looks particularly bright and densely packed, but that very richness comes paired with heavy obscuration. The dust along that line of sight makes peering through it remarkably hard. Working in infrared light, which has the remarkable property of being able to slice through dust far more effectively than ordinary visible light, Stephenson uncovered a star cluster sitting roughly 19,000 light-years from Earth. This was no ordinary cluster. It was packed with some of the most massive and most luminous stars he had ever come across. Red supergiants, blue supergiants, stars churning out hundreds of thousands of times more energy than the Sun manages in a single second. The cluster ended up catalogued as Stephenson 2. And for a long stretch of years afterward, it sat there in the astronomical archives as little more than a curious entry. Just one more massive young cluster among the thousands scattered across our galaxy. But as infrared astronomy matured throughout the 1990s and into the 2000s, as new orbiting observatories like Spitzer and Herschel went operational, astronomers turned their gaze back towards Stephenson 2 with sharper eyes. And what they saw made them pause. One member of that cluster refused to behave like the others. It was outrageously bright in the infrared, far more luminous than any standard red supergiant should reasonably be. Its brightness suggested either that the star was sitting much closer to us than the rest of the cluster, which seemed deeply implausible, or that this was a star of truly extraordinary dimensions. They catalogued it as Stephenson 2 to 18, the 18th star indexed within the cluster. Nobody at that moment realized they were staring at what might very well be the largest star ever uncovered in the universe. That realization arrived later, slowly, as astronomers began the painstaking effort of actually measuring this star's properties in detail. And here is where the difficulty begins. How exactly do you measure a star sitting 19,000 light-years from Earth? You cannot launch a probe and let it fly there. You cannot snap a close-up photograph. You are working entirely with photons of light that have been threading their way through space for 19,000 years before reaching your telescope. Light that left this star around the time when human beings were still living in small hunter-gatherer bands, long before the pyramids, long before written language or agriculture or any kind of organized civilization existed. Those ancient photons finally land on our sensors, and from those single grains of light, we have to reconstruct everything about this distant titan. Its temperature, its brightness, its size, its mass, its chemistry. Everything inferred from light alone. The first step is measuring brightness, and that part is fairly simple. You aim a telescope at the star, gather its light, and quantify how much energy is striking your detector. That gives you what astronomers call apparent magnitude, which describes how bright the star looks from Earth. For Stephenson 2 to 18, the apparent magnitude is rather faint. You will not catch it with the naked eye. Even peering through a small backyard telescope, it gets lost amid the thousands upon thousands of other stars crowding that part of the sky. But the infrared telescopes told a different story. In the infrared, this star burns brilliantly, far brighter than it appears in ordinary visible light. That makes complete sense for a cool star. Cool stars dump most of their energy out as infrared radiation, rather than the visible light we can see with our own eyes. Next comes distance. Brightness on its own is not enough to tell you very much, because a faint nearby star and an enormously bright distant star can both look identical from Earth. You need to know the distance to figure out the actual intrinsic brightness, which astronomers call luminosity. For nearby stars sitting within a few thousand light-years, astronomers rely on parallax. As Earth swings around the Sun across the year, nearby stars appear to wobble ever so slightly against the more distant background of stars. Measuring that minute shift lets you triangulate the distance using nothing more sophisticated than basic geometry. But parallax is only useful for relatively nearby stars. At 19,000 light-years out, the wobble shrinks to a level that is essentially impossible to measure, even with our finest space-based instruments. So astronomers turn to other methods. Since Stephenson 2-18 is part of a cluster, you can estimate the distance to the cluster as a whole by analyzing the properties of multiple stars within it and comparing those measurements to theoretical models. You can pin down the cluster's distance within a range. Different methods produce slightly different answers, which is why distance estimates for Stephenson 2 stretch from somewhere around 17,000 to about 20,000 light-years. We will use 19,000 as our working figure. Now, with brightness and distance both in hand, you can calculate luminosity. How much total energy is the star really pouring out per second? When the calculation finished, the answer was breathtaking. Stephenson 2-18 has a luminosity roughly 440,000 times greater than the Sun's. Every single second, this star pumps out 440,000 times more energy than our own home star. That is an amount of power that genuinely defies easy comprehension. But luminosity alone still does not tell you size. A small, blistering hot star can be enormously luminous. A huge, cool star can also be enormously luminous. To work out the actual size, you need temperature. This is where spectroscopy enters the picture. By splitting the star's incoming light into a spectrum and analyzing which specific wavelengths show up and which are missing, astronomers can determine the temperature of the star's surface. Different temperatures produce distinctive spectral fingerprints. Hot stars display a different pattern of absorption lines than cool stars. The spectrum of Stephenson 2-18 made one fact obvious almost immediately. This is a cool star. Distinctly cool. Its surface temperature sits at only about 3600 Kelvin, which converts to roughly 6,000 degrees Fahrenheit. That might sound scorching, and by everyday standards it certainly is, but for a star it is genuinely cool. Our Sun's surface clocks in at about 5,770 Kelvin, well over 10,000 degrees Fahrenheit, so Stephenson 2-18 is cooler than our Sun. That is exactly why it glows red. Cool stars appear red. Hot stars look blue or white. The spectrum also revealed the presence of certain molecules in the star's atmosphere: titanium oxide, water vapor, carbon monoxide. These molecules can only survive at relatively low temperatures. In hotter stars, they would be ripped to pieces almost instantly. Their presence confirmed without question what astronomers suspected. This is a cool hypergiant. Now comes the crucial calculation. If you know how much total energy a star is emitting, which is its luminosity, and you know its surface temperature, you can work out how large that star must physically be. This relies on a relationship called the Stefan-Boltzmann law. The law tells us that the total energy a star emits depends on two things. First, how hot its surface is, since hotter surfaces radiate more energy per unit area. Second, how much surface area there is. A cool star with a colossal luminosity must possess a colossal surface area to emit that much energy. When astronomers fed the numbers for Stephenson 2-18 into the equations, the answer was staggering. The star's radius came out to somewhere around 2,000 to 400 times the radius of our Sun. Let me put that into perspective. The Sun's radius is about 433,000 miles. Multiply that by 2,000, and you arrive at a radius of roughly 930 million miles. That is the distance just from the star's center out to its surface. The diameter, the full distance across, is about 1,860,000,000 miles. Stephenson 2-18 is the largest star ever observed in the known universe. And now that you understand how astronomers found it and measured it, let us explore what this actually means. A radius of 930 million miles. That number is so vast, it becomes almost meaningless without some kind of anchor. So let us try to make it real. If you could somehow swap our Sun for Stephenson 2-18, leaving everything else in our solar system precisely where it is, here is what the picture would look like. The star's center would sit exactly where the Sun's center currently sits. But instead of the Sun's surface stopping at 433,000 miles from its center, Stephenson 2-18's surface would stretch outward to roughly 10 astronomical units from its center. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So this star's surface alone would reach out to 10 times that distance. Mercury orbits at about 0.4 astronomical units. It would be deep inside the star, completely consumed. Venus at 0.7 astronomical units would also be inside. Earth at 1 astronomical unit. The very ruler we use to measure our solar system would be nowhere near the surface. We would be buried within the star's outer envelope. Mars at 1.5 astronomical units would sit inside it as well. The asteroid belt, hovering between 2 and 3 astronomical units, would be fully contained within the star. Jupiter, the largest planet in our solar system, orbits at about 5.2 astronomical units. Even mighty Jupiter would find itself drifting through the star's glowing atmosphere. Saturn, the ringed giant, orbits at roughly 9.5 astronomical units. Stephenson 2-18's surface would push past Saturn's orbit. If you were standing on Saturn looking up, you would not see a bright pinpoint of light hanging in your sky. You would see a vast, dim red surface stretched across the entire dome of the heavens, glowing like the smoldering coals at the bottom of a fire pit. You would be inside the star. Only Uranus, sitting at 19 astronomical units, and Neptune at 30 astronomical units, would manage to orbit safely outside the stellar surface. The Kuiper belt, that broad reservoir of icy bodies beyond Neptune, would remain in the cool darkness beyond the reach of this cosmic giant. Now let us turn this into volume. The volume of a sphere grows with the cube of its radius. If Stephenson 2-18's radius is roughly 2,000 times the Sun's radius, then its volume is 2,000 cubed. That is 2,000 times 2,000 times 2,000, roughly 10 billion. You could pack about 10 billion suns inside Stephenson 2-18. Not 10, not 100, not a million, 10 billion. If our sun were the size of a tennis ball, Stephenson 2-18 would be a sphere roughly 1,000 feet across, about the height of a 100-story skyscraper. If our sun were a marble, Stephenson 2-18 would be larger than an entire house. The scale is genuinely tough for human minds to wrap around. But here is where the strangeness deepens. Despite being 10 billion times larger in volume, Stephenson 2-18 only contains about 12 to 16 times more mass than our Sun. How is that even possible? The answer is density. Stephenson 2-18 is a member of a colossal star cluster called Stephenson 2, discovered in 1990 by astronomer Charles Bruce Stephenson. The cluster sits in the galactic plane, embedded inside dense regions of interstellar dust and gas. That location makes it remarkably hard to observe, because dust absorbs and scatters incoming light, especially visible light. Early observations of the cluster were conducted with infrared telescopes, since infrared light is far better at piercing through dust than ordinary visible light is. The infrared observations revealed that Stephenson 2 holds some of the most massive and most luminous stars ever catalogued. Among that crowd of titans, one star stood apart. Stephenson 2-18 displayed properties that hinted at a size beyond even the other hypergiants in the same cluster. Measuring the size of a star at this distance requires indirect methods. You cannot just point a telescope at it and read off its diameter the way you might gauge the moon. At 19,000 light-years, even the largest stars in existence collapse into mere points of light. So astronomers combine techniques. First, They measure the star's brightness, the apparent magnitude, which tells us how luminous it appears from Earth. Then they estimate its distance through various methods, often by analyzing the cluster it belongs to. From brightness and distance, you derive luminosity, the total energy output of the star per second. Stephenson 2-18 has a luminosity of about 440,000 times the Sun's. Every second, it floods space with 440,000 times more energy than our own star produces. Next, astronomers measure temperature by analyzing the spectrum, the way the star's light spreads out into different colors. Different temperatures yield different spectral signatures. Stephenson 2-18 has a surface temperature of roughly 3,600 Kelvin, or about 6,000 degrees Fahrenheit. As mentioned, that is hot but cool for a star. Our Sun's surface clocks at 5,770 Kelvin, or about 10,000 degrees Fahrenheit. So Stephenson 2-18 is cooler than the Sun, which is why it shines red rather than yellow-white. Cool stars look red, hotter stars look blue or white. Once you have luminosity and temperature, you can calculate radius using the Stefan-Boltzmann relationship, which links a star's luminosity to its temperature and its surface area. A cool star with massive luminosity must have a massive surface area to emit that much energy. The calculations for Stephenson 2-18 produce a radius somewhere between 2,000 and 400 times the Sun's radius. The uncertainty creeps in because measuring the exact temperature and luminosity at such enormous distance always introduces error margins. Even at the conservative end of the estimates, this star is mind-bendingly large. 2,000 solar radii equals roughly 930 million miles in radius, or 1,860,000,000 miles in diameter. At the upper end, 400 solar radii, the radius reaches around 1,120,000,000 miles, with a diameter of roughly 2,240,000,000 miles. Either way, it is the largest star we have ever found. There are other contenders. Stars like UY Scuti, VY Canis Majoris, and WOHG 64 have all been put forward as candidates for the largest known star at various points in time. Measurements keep getting refined as better instruments come online and better data becomes available. For a stretch of years, UY Scuti held the title with radius estimates around 1,700 solar radii, but later, more precise measurements brought that figure down to about 755 solar radii, making it considerably smaller than originally thought. Stephenson 2-18, based on the best current estimates, appears to be larger, but astronomy is a science of constant refinement. Future observations with improved instruments could yet shift these numbers around. What we can say with real confidence is that Stephenson 2-18 ranks among the largest stars ever discovered and very likely sits at the top of the list. Now here is a question worth asking. Why are there limits on how large a star can get? You might assume that with enough mass, you could just keep stacking material until you built an arbitrarily enormous star, but stellar physics simply does not work that way. There are hard ceilings imposed by the fundamental forces of nature. Stars shine because of nuclear fusion happening in their cores. Hydrogen atoms slam together and fuse into helium, releasing energy in the process. That energy creates outward pressure that pushes against the inward pull of gravity. A star is essentially a constant battle between these two forces. Gravity is always trying to crush the star inward. Fusion pressure is always trying to blow it outward. When the two are balanced, the star sits stable. But very massive stars, those with more than about 8 to 10 times the Sun's mass, live fast and die young. They burn through their fuel at frantic rates. The more massive a star is, the hotter and denser its core has to be in order to generate enough pressure to support itself against gravity. That higher core temperature means fusion proceeds more rapidly. Massive stars exhaust their hydrogen reserves in just a few million years instead of billions. When the hydrogen runs out in the core, they begin fusing helium into carbon. When helium runs out, they fuse carbon into still heavier elements. The process keeps marching up the periodic table, producing oxygen, neon, magnesium, silicon, and eventually iron. Each successive stage releases less energy than the last and unfolds faster. A massive star might spend millions of years burning hydrogen, thousands of years burning helium, hundreds of years burning carbon, and just days fusing silicon into iron. Iron is where the line is drawn. Fusing iron, does not release energy, it absorbs energy. So once a massive star builds up an iron core, fusion shuts down. The outward pressure vanishes, gravity wins. The core collapses in a fraction of a second, triggering a supernova explosion. Now here is the key piece for understanding size limits. As a star evolves off the main sequence and starts fusing heavier elements, it expands. The core contracts and heats up, but the outer layers expand and cool. This is why old, massive stars become red supergiants, or, in the most extreme cases, hypergiants. Stephenson 2-18 is a hypergiant. It is in a late stage of stellar evolution, approaching the end of its life. It has bloated to an enormous size because its core is contracting while its envelope expands. But there is a limit to how far this expansion can go. That limit comes from something called the Eddington limit. This is the threshold where the outward pressure from radiation grows so intense that it overcomes gravity and starts blowing the star apart. Stars emit light, and light carries momentum. When photons stream outward from a star, they push on the atoms in its outer layers. In ordinary stars, this radiation pressure is negligible compared to gravity. But in extraordinarily luminous stars, radiation pressure becomes a serious player. In hypergiants like Stephenson 2-18, radiation pressure is enormous. The star is emitting 440,000 times more light than the Sun. All those photons surging outward are physically pushing on the star's outer layers. If the star got any brighter for its mass, the radiation pressure would exceed gravity. The outer layers would be torn loose and flung into space. This is exactly what happens in the most massive stars. They shed mass through powerful stellar winds, losing material continuously. Stephenson 2-18 is almost certainly losing mass this way. Its outer envelope is likely being progressively stripped away by its own radiation. Eventually, the star will lose so much mass that it can no longer maintain its enormous size. It will collapse, trigger a supernova, and most likely leave behind either a neutron star or a black hole. So the size limit for stars is not really about how much mass you can pile up. It is about the balance between gravity, radiation pressure, and the star's evolutionary state. Stephenson 2-18 sits perched right at that limit. Any larger, and it would probably blow itself apart. Let us imagine what it would actually be like to visit this star, hypothetically. Picture yourself in a spacecraft approaching Stephenson 2-18 from a distance of several astronomical units. The star would dominate your entire field of view. It would not look like a point of light anymore. It would look like a vast, glowing wall stretched across the sky. As you close the distance, the star's reddish hue would become more pronounced. This is a cool star by stellar standards, glowing red-orange rather than white or blue. The surface would actually appear dim compared to the Sun. Despite being 440,000 times more luminous in total, that light is spread across such an enormous surface area that the surface brightness is actually quite low. If you could somehow stand on a platform right at the star's surface and look around, the local environment would not be blindingly bright. It would glow dully, like coals smoldering in a fireplace. You could possibly look directly at the surface without your eyes being instantly destroyed, although the infrared radiation would still cook you to death rather quickly. The real danger would not be the visible light. It would be heat. Even though the surface temperature is only around 600 Kelvin, the sheer volume of radiation being pumped out would incinerate anything close by. At the distance of Earth's orbit from the center of this star, assuming you could somehow survive inside the outer envelope, the temperature would be several thousand degrees. Everything would be plasma. No solid matter could exist. As you move deeper toward the core, temperatures would climb into the millions of degrees. The core of Stephenson 2-18, where fusion is taking place, likely reaches temperatures of several hundred million degrees Kelvin. At those temperatures, matter breaks down into bare nuclei and free electrons. The pressure is millions of times higher than Earth's atmospheric pressure. Nothing remotely resembling a physical structure could persist there. It is a realm of pure energy and fundamental particles. Now, one of the most striking things about Stephenson 2-18 is how transient its existence really is. Stars like this are rare not just in space but also in time. Our Sun has a total lifetime of about 10 billion years. It is currently around 4.6 billion years old, roughly halfway through its run. It will keep fusing hydrogen for another 5 billion years or so before exhausting its fuel and bloating into a red giant. Stephenson 2-18, in stark contrast, will live perhaps 20 million years total. Maybe less. It might already have exploded as a supernova and we simply do not know it yet, because the light from that explosion is still racing toward us. Remember, the star is 19,000 light-years away. What we see today is what the star looked like 19,000 years ago. If it exploded 10,000 years ago, we would not learn of it for another 9,000 years. This temporal asymmetry is one of the strange consequences of looking at things light-years away. You are always peering into the past. When Stephenson 2-18 finally does explode, and it will, the explosion will be spectacular. Hypergiants like this are believed to end their lives as supernovae, possibly even as hypernovae, which are essentially supernovae on steroids. A hypernova releases more energy than an ordinary supernova, possibly enough to generate a gamma-ray burst. Gamma-ray bursts are the most energetic events in the universe outside of the Big Bang itself. They release more energy in a few seconds than our Sun will emit across its entire 10 billion-year lifetime. If Stephenson 2-18 produces a gamma-ray burst when it dies, and if that burst happens to be aimed in our direction, it could be visible from Earth even at 19,000 light-years away. It would appear as an incredibly bright point of light in the constellation Scutum, potentially visible during daytime for a brief period. But we do not have to worry about danger. At 19,000 light-years, the radiation would be dispersed and absorbed by interstellar material long before reaching Earth. We would be perfectly safe. We would just get a spectacular light show. The supernova remnant would expand outward at a significant fraction of the speed of light, plowing into surrounding gas and forming a glowing nebula. That nebula would remain visible for thousands of years, slowly fading as it cooled and dispersed. The core would collapse. Given the star's estimated mass, somewhere between 12 and 16 solar masses, it sits right on the borderline between forming a neutron star and forming a black hole. Neutron stars form from cores between roughly 1.4 and 3 solar masses. Above that, the core collapses all the way to a black hole. Stephenson 2-18's fate depends on how much mass it has shed through stellar winds. If it has lost enough, the surviving core might form a neutron star. If it has retained most of its mass, the result could be a black hole. Either way, the hypergiant itself will be gone, replaced by a compact remnant. Let us put Stephenson 2-18 into perspective, alongside other extreme stars, to give you a real feel for how unusual it actually is. Our Sun is a G-type main sequence star, fairly average in size and mass. Most stars in the galaxy are actually smaller and cooler than the Sun. Red dwarfs, the smallest stars capable of sustaining fusion, account for about 70% of all stars. A typical red dwarf might have a radius of only 10 to 20% of the Sun's, with a mass perhaps 10 to 50% of the Sun's mass. Red dwarfs are tiny, dim, and incredibly long-lived. The smallest among them will keep burning for trillions of years. At the opposite extreme, you have blue supergiants and hypergiants. These are massive, scorching hot, and stunningly luminous. Rigel, the bright blue star in Orion's foot, is a blue supergiant with a radius about 79 times the Sun's. It is enormous compared to the Sun, but utterly minuscule next to Stephenson 2-18. Then there are red supergiants, cooler stars, that have swollen to colossal sizes. Betelgeuse, the red star marking Orion's shoulder, is perhaps the most famous red supergiant. Its radius varies because the star pulsates, but estimates place it somewhere around 764 solar radii. That is huge. If you placed Betelgeuse where the Sun is, its surface would extend past Mars's orbit, possibly reaching the asteroid belt. But Stephenson 2-18 is still nearly 3 times larger. Antares, another celebrated red supergiant in the constellation Scorpius, has a radius of about 680 solar radii. VY Canis Majoris, one of the largest known red supergiants, comes in at around 1/500 solar radii, still smaller than Stephenson 2-18. UY Scuti, which was for a time considered the largest known star, currently measures around 755 solar radii, although earlier estimates were significantly higher. The point is, Even among the largest stars, Stephenson 2 to 18 stands apart. It sits in a class of its own. There is, however, an important caveat to mention here. Measuring stellar radii, especially for distant red hypergiants, is extraordinarily challenging. These stars are often shrouded in thick clouds of dust expelled from their own surfaces. The dust absorbs and scatters light, making it difficult to determine where the star's true surface really lies. On top of that, many of these stars pulsate, expanding and contracting over months or years. Their size is not even constant. Stephenson 2 to 18 might be larger at certain times and smaller at others. The measurements we have are essentially snapshots, and they come with error bars. The radius range of 2000 to 2400 solar radii is just that, a range, not a precise number. Future observations with better instruments may refine it further. It is possible another star will be found that is larger. It is equally possible that improved measurements will reveal Stephenson 2 to 18 to be smaller than currently believed. But based on the best data available right now, it is the largest. Let us talk about the cluster this star calls home. Stephenson 2 is an open cluster, a group of stars that form together from the same molecular cloud. The cluster is young by stellar standards, only about 20 million years old. It contains some of the most massive stars in the galaxy, including multiple red supergiants and hypergiants. Its location in the galactic plane means it is embedded in dense star-forming regions. There is active star formation happening nearby. The environment is rich in the gas and dust that serve as raw materials for making new stars. Stephenson 2 is believed to be one of the most massive young clusters in the entire Milky Way, containing an estimated 50,000 to 100,000 solar masses worth of stars. Some of its other notable members include Stephenson 2 to 3, another red hypergiant, and Stephenson 2 to 7, which is also a red supergiant. These are all massive stars in late evolutionary stages. Within a few million years, many of them will explode as supernovae. The cluster will eventually be torn apart by these explosions and by gravitational interactions. Young clusters like Stephenson 2 do not last forever. Across tens of millions of years, the stars drift apart, dispersing into the general galactic population. So the cluster we see today is a temporary association. It is a snapshot of a brief moment in our galaxy's history when a particular collection of massive stars happened to be in the same place. In 100 million years, Stephenson 2 as a recognizable cluster will not exist anymore. Its stars will be scattered across a wide region of the galaxy, but the legacy these stars leave will remain. When they explode, they will enrich the interstellar medium with heavy elements. Carbon, oxygen, nitrogen, silicon, iron, and dozens of others, all forged in their cores or during their supernova detonations. Those elements will become part of new clouds of gas and dust. Those clouds will collapse to form new stars and planets. The atoms in your body, the iron in your blood, the calcium in your bones, the oxygen in your every breath, all of it was created in stars. Most of it was created in stars like Stephenson 2 to 18. Massive stars are the universe's element factories. They are where the complexity of chemistry actually gets built. Without massive stars, the universe would consist only of hydrogen and helium. No rocky planets, no water, no life. Stars like Stephenson 2 to 18 are rare, but they are essential to the universe's capacity to generate complexity. They live fast, die young, and in their death throes they seed the cosmos with the building blocks of all the worlds yet to come. Now let us tackle a common question. Could life exist on a planet orbiting a star like Stephenson 2 to 18? The short answer is no. Not in any form we would recognize. First, the star's lifetime is far too brief. Life as we understand it took billions of years to develop on Earth. Simple, single-celled organisms appeared about 3.8 billion years ago. Complex multicellular life did not show up until about 600 million years ago. Intelligent life is even more recent. A star like Stephenson 2 to 18 will only live for about 20 million years total. That is nowhere near enough time for life to evolve from chemistry. Second, the environment around such a star is brutally hostile. Even if a planet had somehow formed in orbit before the star inflated into a hypergiant, which is unlikely, the planet would be subjected to crushing radiation. The star's luminosity fluctuates as it pulsates. The stellar wind would strip away any atmosphere. When the star ballooned outward into a hypergiant, it would have engulfed any planets in close orbits. Planets that started out in the original habitable zone would have been vaporized as the star expanded. Third, massive stars like this emit large quantities of ultraviolet radiation and X-rays. This high-energy radiation tears apart molecules, making it extremely difficult for complex chemistry to survive on any nearby world. The only way a planet could possibly be habitable around a star like this would be if it orbited extraordinarily far away, many astronomical units beyond the bloated envelope. But even then, the star's lifetime would be too short and the radiation environment too harsh. So no, planets around hypergiants are not promising places to hunt for life. Life, as far as we currently understand it, requires stable conditions sustained over long timescales. It needs a star that will shine steadily for billions of years, providing consistent energy. It needs liquid water, organic molecules, and protection from radiation. Hypergiants offer none of these things. They are spectacular objects, crucial to the universe's chemical evolution, but they are not homes for life. The best places to look for life are around stars like the Sun, medium-mass stars that burn steadily for billions of years and provide stable energy across geological timescales, or possibly around red dwarfs, the smallest stars, which burn for trillions of years, although they bring their own complications with flares and tidal locking. Hypergiants are fascinating, but they are factories, not nurseries. They make the elements life needs, but they do not host life. Here is another angle worth thinking about. What if you could harness the energy of a star like Stephenson 2-18? The concept of a Dyson sphere, a megastructure surrounding a star to capture all of its energy, was first proposed by physicist Freeman Dyson in 1960. The idea was that an advanced civilization could construct a swarm of solar collectors orbiting a star, intercepting a significant fraction of its total output. For a star like the Sun, this would supply enormous amounts of power, far more than humanity currently consumes. For a star like Stephenson 2-18, the energy on offer would be staggering. Remember, this star produces 440,000 times more energy than the Sun. Capturing even a tiny sliver of that flow would yield power on a scale almost beyond comprehension. But constructing a Dyson sphere around Stephenson 2-18 would be impractical for several reasons. First, the star's lifespan is simply too short. By the time you finished building the megastructure, the star would already be approaching the end of its life. You would invest enormous resources into a project that could only function for a few million years at most before the star detonated and obliterated everything. Second, the star is so vast that the amount of material needed to build a structure around it would be prohibitive. To assemble a solid shell around a star with a 2 billion mile diameter would require more raw material than exists in the entire solar system. You would need to dismantle thousands of planetary systems just to gather enough construction material. Third, the star's intense radiation and ferocious stellar winds would make construction and maintenance nearly impossible. Any structure would be subjected to constant bombardment by high-energy particles and radiation. It would have to be incredibly robust, far beyond anything we can currently imagine. A more sensible approach would be to build your Dyson sphere around a stable, long-lived star. A star like the Sun, or even a red dwarf. Stars that will shine steadily for billions of years and provide reliable energy across the entire history of a civilization. Stephenson 2-18 is impressive, but it is not a good candidate for long-term energy harvesting. It is too unstable, too short-lived, too violent. Now let us pull the camera back and think about the role stars like Stephenson 2-18 play in our galaxy's evolution. The Milky Way has been forming stars for over 13 billion years. Across that immense span of time, countless generations of stars have been born, lived, and died. The very first stars, called population 3 stars, formed from pure hydrogen and helium. No heavy elements existed yet because heavy elements can only be made inside stars. These first stars were probably very massive, burning hot and fast, exploding as supernovae after just a few million years. Their explosions seeded the universe with the first heavy elements: carbon, oxygen, nitrogen, silicon, magnesium, iron. These elements mixed with the surviving hydrogen and helium, creating chemically enriched gas clouds. The next generation of stars, population 2, formed from this slightly enriched material. They contained a small fraction of heavy elements, just enough to allow more complex chemistry in any surrounding material. Our Sun is a population I star, a member of the most recent generation. It formed about 4.6 billion years ago from gas that had already been enriched by multiple previous generations of stars. The planets of the solar system, including Earth, formed from material containing about 2% heavy elements by mass. That 2% came entirely from previous stars. Stars like Stephenson 2-18 are part of this ongoing cycle. When it explodes, it will scatter heavy elements into the interstellar medium. Those elements will eventually become part of new stars and planets. This is how the galaxy gradually grows more metal-rich across cosmic time. Astronomers refer to any element heavier than helium as a metal, even though most of them are not metals in the chemistry sense of the word. When astronomers say a star is metal-rich, they mean it contains a higher fraction of elements heavier than helium. Metal-rich stars are younger. They formed from gas that had been processed through multiple earlier generations of stars. Metal-poor stars are older. They formed from gas that had been less enriched. Stephenson 2-18 is a young, metal-rich star. It formed from gas that already contains substantial amounts of heavy elements from previous generations, and when it dies, it will dump even more heavy elements into the mix, contributing to the galaxy's continuing chemical evolution. This entire process is why the universe is capable of generating complex structures. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Everything else, every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in Earth's core, all of it was forged inside stars. Most of it was forged inside massive stars like Stephenson 2-18. These stars are the universe's alchemists. They take simple elements and shape them into complex ones. They live briefly but brilliantly, and in their death they enrich the cosmos. Without them, the universe would be a far simpler, far less interesting place. Let us think about observation. How do we actually study a star like Stephenson 2-18? It is not as if we can send a probe to it. At 19,000 light-years away, even traveling at the speed of light, it would take 19,000 years to arrive. No spacecraft we have ever built could possibly make that trip. Voyager 1, our fastest and most distant probe, has been traveling for over 47 years and has only covered about 0.002 light-years. At that pace, it would take millions of years to reach Stephenson 2-18. So instead, we study it from afar using telescopes. We collect light from the star, split that light into a spectrum, and analyze the patterns. Different elements absorb and emit light at specific wavelengths. By examining which wavelengths are present or missing, we can determine the star's composition, its temperature, its velocity, and other properties. We can also track the star's brightness over time to see whether it varies. Many red hypergiants are variable stars, meaning their brightness shifts periodically. This variability is driven by pulsations. The star expands and contracts, changing its size and temperature, and therefore its brightness. By monitoring these variations, we learn about the star's structure and its dynamics. Some observations are conducted in visible light, but many are done in the infrared. Stephenson 2-18 is heavily obscured by dust, both from the cluster itself and from the interstellar medium between us and the star. Infrared light pierces through dust far more effectively than visible light, allowing us to see through that obscuration. Radio observations can also be useful. Stars emit radio waves, and calming those waves reveals information about stellar winds, magnetic fields, and other phenomena. Interferometry, the technique of combining light from multiple telescopes to act as one larger telescope, can achieve higher resolution than any single instrument. This technique has been used to directly measure the sizes of some nearby giant stars. For stars as distant as Stephenson 2-18, interferometry is challenging but potentially possible with sufficiently long baselines. Most of what we know comes from photometry and spectroscopy. Photometry is measuring brightness, spectroscopy is measuring the spectrum. Together, they paint a remarkably complete picture of a star's properties. We can derive its temperature, luminosity, composition, mass, radius, age, and evolutionary state, all from light gathered across 19,000 light-years of empty space. It is a testament to human ingenuity and the power of physics that we can learn so much about an object we will never physically reach. Here is something to ponder. How many stars like Stephenson 2 to 18 actually exist in the galaxy? The answer is not many. Hypergiants are exceedingly rare. Out of the hundreds of billions of stars in the Milky Way, only a few dozen hypergiants have been identified. This rarity stems partly from the fact that hypergiants are genuinely uncommon, and partly from the fact that they are so hard to find. They are often shrouded by dust, located in distant or crowded regions, and they do not live long. Even if the galaxy produces a hypergiant every few thousand years, each one only persists for a few million years. That means at any given moment, there might only be a few thousand of them spread across the entire galaxy, and most are too distant or too obscured for us to detect. The ones we have identified are mostly nearby, within a few tens of thousands of light-years. Stephenson 2 to 18 at 19,000 light-years is one of the more distant ones we have studied in any detail. There are almost certainly other hypergiants farther out, hidden from us by distance and dust. We will probably discover more as our instruments improve and our surveys cover more of the sky. But hypergiants will always remain rare. They represent a brief, extreme phase in the lives of the most massive stars. Most stars never become hypergiants because they simply are not massive enough. Only stars with initial masses above roughly 20 to 25 solar masses can evolve into hypergiants, and even then, only under certain conditions. Most massive stars actually explode as supernovae while still in the blue supergiant phase. Only some manage to evolve into red supergiants, and only a fraction of those become hypergiants. So Stephenson 2 to 18 is a rare object, a glimpse into the extreme end of stellar evolution, a star that has pushed the limits of size right up to the breaking point. Let us return to that visualization we started with. Imagine yourself standing on Earth, looking up at the night sky. Now imagine that, instead of the sun, Stephenson 2 to 18 sits at the center of our solar system. The sky would be utterly transformed. During the day, you would not see a bright point of light overhead. You would see a vast, dim red disk filling a huge portion of the heavens. The star's surface would be close enough that it would appear as a disk, not a point. And because you would be inside the star's outer envelope, the sky would be filled with glowing gas. Of course, Earth would not exist in this scenario. The planet would have been vaporized when the star expanded, but if you could somehow have a platform floating in space at the distance where Earth normally orbits 1 astronomical unit from the center, you would be deep inside the star's atmosphere. The temperature would be thousands of degrees. The pressure would be immense. You would be surrounded by glowing plasma. Looking outward, you would see a gradually brightening glow toward the star's core and a dimming glow toward the surface. There would be no sharp boundaries, no clear sense of up or down, just an endless sea of luminous gas in every direction. It is a vision of hell in some ways, an environment utterly hostile to anything resembling life or structure. And yet it is also a place of creation. This is where heavy elements are being forged, where the raw materials for future planets and future life are being assembled. The same processes that make this environment lethal are the processes that allow the universe to produce complexity. Fusion in the core, convection in the envelope, mass loss through stellar winds, and eventually a supernova that will scatter enriched material across light-years of space. These are not merely destructive processes, they are constructive. They are the means by which the universe builds the chemical foundation for everything that comes after. Stephenson 2 to 18 will not last. Within a few million years, possibly within the next million, it will explode. The explosion will be visible from Earth as a brilliant new star appearing in the constellation Scuti. It will outshine most of the stars in the night sky for weeks or months before gradually fading. The remnant will expand outward, eventually forming a nebula that might remain visible for thousands of years, and then slowly that nebula will disperse. The elements created in the star and in the supernova will mix with the interstellar medium. New stars will form from that enriched material. Some of those stars will host planets. Some of those planets might develop life. And if they do, that life will owe its existence in part to Stephenson 2 to 18. The carbon in its molecules, the oxygen in its atmosphere, the iron in its core, all of it will have been created in stars like this one. This is the legacy of hypergiants. They do not leave behind stable systems or long-lived structures. They leave behind enriched material, the seeds of future complexity. Now, before we wind toward the end, let us consider what Stephenson 2 to 18 means for our understanding of the universe. This star challenges our models of stellar evolution. Stars this large should not even be stable, and yet they exist. They should blow themselves apart under the pressure of their own radiation. And yet, they hold together, at least for a while. Studying stars like this helps refine our theories. It shows us the extremes, the edge cases where our models get tested. Every observation of a hypergiant gives us more data, more constraints on the underlying physics. And there is still a great deal we do not understand. We do not fully grasp the mass loss mechanisms. How exactly does a hypergiant shed mass through stellar winds? What drives those winds? How much mass is lost over the star's lifetime? We do not fully understand the internal structure. What is happening in the core? How does convection operate in a star this large and this diffuse? Are there layers or shells of different compositions? We do not fully understand the end state. Will Stephenson 2 to 18 explode as a normal supernova, or will it produce something more exotic? Could it collapse directly into a black hole without producing a visible explosion at all? These are open questions, and the only way to answer them is to keep observing, keep building better instruments, keep refining the models. Stephenson 2 to 18 is one data point in a much larger effort to understand how stars work. But it is a particularly important data point because it represents the extreme. And understanding the extremes helps us understand the full range of behavior. If we only studied stars like the Sun, we would have a deeply incomplete picture. We need to study the smallest stars, the largest stars, the hottest, the coolest, the youngest, the oldest. Every type of star teaches us something different. Hypergiants teach us about the limits. How large can a star become? How luminous? How unstable? What happens when you push physics to its breaking point? Stephenson 2 to 18 is an answer to some of those questions and a fresh source of new ones. Let me explain more about what makes red hypergiants specifically so fascinating. These stars exist within a very narrow evolutionary phase. They are massive stars that have exhausted the hydrogen in their cores and have moved on to fusing heavier elements. But they have not yet reached the final stages that lead to supernova. They are in transition, and that transition produces unique conditions. The core of a red hypergiant is contracting and heating up as it fuses helium into carbon and oxygen. This contraction releases gravitational energy that heats the surrounding layers. Those outer layers respond by expanding dramatically. It is counterintuitive, but that is how stellar physics works. A contracting core leads to an expanding envelope. The envelope swells so much that it cools off significantly. The surface temperature drops from tens of thousands of degrees, typical of a main sequence massive star, down to just a few thousand degrees for a red hypergiant. This cooling causes the star to glow red instead of blue or white. But despite the cooler surface, the total energy output actually increases. The star becomes more luminous because the surface area is so enormously larger. Think of it this way. A small piece of hot metal radiates a certain amount of energy. A huge piece of warm metal might radiate much more total energy, even though each square inch is cooler. That is exactly what is happening with red hypergiants. The surface is cooler per unit area, but there is so much more surface area that the total output is staggering. Now, one of the most fascinating things about these stars is their instability. Red hypergiants are not stable objects. They pulsate. They vary in brightness. They shed mass erratically. The outer envelope is so loosely bound that it is constantly being lost to space. Powerful stellar winds carry material away at rates that would horrify any engineer trying to build a stable system. Some estimates suggest Stephenson 2 to 18 might be losing mass at a rate of about 1/10,000th of a solar mass per year. That might not sound like much, but spread across a million years, That is 100 solar masses, more material than many entire stars contain. This mass loss has profound consequences. It means the star is constantly getting smaller, shedding its outer layers. It also means the space surrounding the star is filled with previously ejected material. This creates a circumstellar envelope, a cloud of gas and dust enveloping the star. When we observe Stephenson 2 to 18, we are not just seeing the star itself. We are seeing the star plus this surrounding material. That makes precise measurements even more difficult, because you have to account for the contribution from circumstellar material. Some of that material is being driven outward by radiation pressure. Photons from the star strike dust grains and atoms in the envelope, transferring momentum. This pressure pushes the material outward, creating a wind. But it is not a smooth, steady wind. It is clumpy, variable, and irregular. Observations show that red hypergiants can have large-scale convection cells on their surfaces. These are rising and falling currents of hot and cool gas, similar to the convection you see in boiling water, but on an unimaginably larger scale. A single convection cell might be larger than the entire orbit of Earth around the Sun. These convection cells generate hot spots and cool spots on the star's surface. As the star rotates, albeit slowly, these spots rotate in and out of view. This causes brightness variations that we can measure from Earth. By studying these variations, astronomers learn about the star's rotation rate, its surface structure, and the physics of convection at extreme scales. Another source of variability comes from pulsations. The star expands and contracts over periods of months or years. During expansion, the surface moves outward, the star grows larger, and the temperature drops slightly. During contraction, the opposite happens. These pulsations are driven by the kappa mechanism, a feedback loop in which increased opacity in the star's outer layers causes them to absorb more radiation, heat up, expand, then cool, and contract again. It is essentially a natural oscillation, like a spring bouncing up and down. For Stephenson 2 to 18, these pulsations might shift the star's radius by 10 or 20% across the course of a year or two. That means the star could vary from about 1/800 solar radii to 2/200 solar radii over a single pulsation cycle. Measuring these variations helps astronomers understand the star's interior, since the pulsation period depends on the star's mass, radius, and internal density distribution. Now let us think about the star's magnetic field. Most stars have magnetic fields generated by dynamo processes operating in their interiors. The Sun has a magnetic field that produces sunspots, flares, and coronal mass ejections. Red hypergiants likely have magnetic fields too, though they are much harder to measure because the stars are so distant. The magnetic field in a red hypergiant would be shaped by the star's rotation and convection. As convection cells rise and fall, they drag magnetic field lines along with them, creating tangled, complex magnetic structures. These magnetic fields might play a role in driving mass loss. They could channel material away from the star along field lines, similar to the way the Sun's magnetic field channels solar wind. They might also create hotspots where magnetic field lines concentrate energy, heating localized patches of the star's atmosphere. Those hotspots could contribute to the X-ray emission that has been detected from some red hypergiants. X-rays from a cool star might seem contradictory, but magnetic activity can produce small regions of extremely hot plasma even within an otherwise cool stellar atmosphere. The study of red hypergiant magnetic fields is an active area of research. Better instruments, particularly spectropolarimeters that can measure the polarization of light caused by magnetic fields, are helping astronomers map these fields. Each new observation adds to our understanding of how these extreme stars actually work. Let us talk about some specific comparisons to help you genuinely grasp the scale we are dealing with. Stephenson 2-18's radius is roughly 930 million miles. Let us break that down into different units to view it from multiple angles. In astronomical units, it is about 10 astronomical units. Remember, 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. So this star's radius alone is about 10 times the Earth-Sun distance. Its diameter, therefore, is about 20 astronomical units. Neptune, the outermost planet in our solar system, orbits at about 30 astronomical units from the Sun. If you placed Stephenson 2 to 18 at the center of our solar system, its surface would extend most of the way out to Neptune's orbit. Pluto, the dwarf planet, orbits at an average distance of about 39 astronomical units. Pluto would still safely orbit outside the star. The Kuiper Belt, the region of icy objects beyond Neptune, starts at around 30 astronomical units and extends to roughly 50 astronomical units. The Kuiper Belt would remain safely outside the stellar surface. Only objects within about 10 astronomical units of the central position would be engulfed. Now, let us think about time. Light travels at roughly 186,000 miles per second. In 1 second, light can circle Earth's equator about 7.5 times. Light takes about 8 minutes and 20 seconds to travel from the Sun to Earth. How long would it take light to cross Stephenson 2-18's diameter? The diameter is about 1,860,000,000 miles. Light travels at 186,000 miles per second. Divide 1,860,000,000 by 186,000, and you get approximately 10,000 seconds. That is about 2 hours and 47 minutes. Light would take about 2 hours and 47 minutes to travel from one side of Stephenson 2 to 18 to the other. Compare that to the Sun, where light takes only about 4.6 seconds to cross the diameter, or Earth, where light takes about 0.042 seconds to cross. This star is so vast that light, the fastest thing in the universe, takes more than 2 hours to traverse it. If you were somehow standing at the center of Stephenson 2 to 18 and you fired a light signal toward the surface, it would take about 1 hour and 24 minutes to arrive. By that time, conditions might have changed significantly in the star's dynamic outer layers. Another comparison involves mass. We have said Stephenson 2 to 18 contains about 12 to 16 times the Sun's mass. The Sun's mass is approximately 2 times 10 to the 30 kilograms. That is a 2 followed by 30 zeros. It is about 330,000 times Earth's mass. So Stephenson 2 to 18 contains somewhere between 24 and 32 times 10 to the 30 kilograms. That is equivalent to somewhere between 4 million and 5.3 million Earths. But remember, this mass is spread across a volume 10 billion times larger than the Sun. The average density is therefore about 1 billion times lower than the Sun's. The Sun has an average density of about 1.4 grams per cc, slightly higher than water. Stephenson 2-18's average density is about 0.0000014 grams per cc. That is 1.4 millionths of a gram per cc. For comparison, the best vacuum we can produce in laboratories on Earth is about 1 trillionth of a gram per cc. So even the star's average density is thousands of times higher than laboratory vacuum, but it is incredibly low by stellar standards. The core would be much denser, perhaps approaching or exceeding the Sun's core density. But the outer envelope is extraordinarily thin, almost nothing by any terrestrial standard. Now let us explore the historical context of red hypergiant discovery. For most of human history, the stars were thought to be unchanging, eternal points of light. The ancient Greeks called them the fixed stars, distinguishing them from the wandering stars, which were the planets. It was not until the Renaissance that astronomers began to realize stars could change. In 1572, Tycho Brahe observed a new star that appeared in the constellation Cassiopeia. It was brighter than Venus at its peak and was visible during the day. This was a supernova, although the term would not be coined for centuries. In 1604, Johannes Kepler observed another supernova, this time in the constellation Ophiuchus. These observations challenged the idea that the heavens were unchanging. But the nature of stars themselves remained a mystery. Were they other suns like ours? Were they completely different types of objects? How far away were they? These questions did not get answered until the 19th and 20th centuries. The development of spectroscopy in the mid-1800s allowed astronomers to analyze starlight in detail. By splitting light into its component colors, scientists could identify which elements were present in a star's atmosphere. Different elements absorb and emit light at specific wavelengths, creating distinctive patterns. This technique revealed that stars are made mostly of hydrogen and helium, the same elements found on Earth, but in different proportions. It also revealed that stars come in different temperatures. Hot stars are blue, cool stars are red. In the early 1900s, Astronomers Ejnar Hertzsprung and Henry Norris Russell independently developed what is now called the Hertzsprung-Russell diagram. This is a graph that plots a star's luminosity against its temperature. When you plot thousands of stars on this diagram, patterns emerge. Most stars fall along a diagonal band called the main sequence, where our Sun sits. But some stars lie off the main sequence. These are giants and supergiants, stars that are much more luminous than main sequence stars of the same temperature. Red giants and red supergiants occupy the upper right corner of the diagram. High luminosity but cool temperature. As telescopes improved and surveys cataloged more stars, astronomers found that the red giant region extends to extraordinarily high luminosities. Some stars are so luminous they dwarf anything else in their vicinity. These ultra-luminous cool stars eventually got classified as hypergiants. The term hypergiant was coined to distinguish them from regular supergiants. They are not just bigger, they are in an entirely different category of extremity. Early examples included stars like UY Scuti, discovered in the 1930s to be a red supergiant with an enormous radius. Mu Cephei, also known as Herschel's garnet star because of its deep red color, was another early known red supergiant. VY Canis Majoris was long believed to be the largest known star, with radius estimates in the 1990s suggesting it might be up to 2,800 solar radii. Later measurements revised that estimate downward to about 1,420 solar radii. Still enormous, but not quite as large as originally thought. This pattern of revising estimates is common in astronomy. As instruments improve and techniques get better, measurements grow more accurate. Early estimates often have large uncertainties, and sometimes the true value turns out to be quite different from initial guesses. UY Scuti was another contender for the largest star, discovered in the 1860s. It was not until modern infrared observations that its true size was appreciated. Initial estimates suggested radii as high as 1/900 solar radii. Current estimates are lower, around 755 solar radii. Stephenson 2-18 entered this competition relatively recently. The cluster was discovered in 1990, but detailed studies of individual stars within it came later. It was not until the 2000s and 2010s that high-resolution infrared observations allowed astronomers to measure the properties of stars within the cluster accurately. Stephenson 2-18 emerged as a strong candidate for the largest known star based on those observations. Its large radius, combined with relatively high confidence in the measurements, puts it at or near the top of the list. But the competition continues. Astronomy is an ongoing process. New stars are discovered. Old measurements get refined. The rankings shift. What we can say is that Stephenson 2-18 ranks among the largest stars ever found, and quite possibly is the very largest. Future observations will continue to refine our understanding. Let us think about the technology that allows us to study stars like this. Observing Stephenson 2-18 requires specialized instruments. Optical telescopes struggle because the star is heavily obscured by dust. The cluster sits in the galactic plane, the disk of the Milky Way, where most of the galaxy's gas and dust is concentrated. Between us and Stephenson 2, there is a substantial amount of intervening material. This material absorbs blue and green light preferentially, allowing red light to pass through more easily. This is why the night sky appears darker in some directions than others. Why the band of the Milky Way shows dark lanes and bright patches. Those dark lanes are dust clouds blocking the light from stars behind them. To see through this dust, astronomers use infrared telescopes. Infrared light has longer wavelengths than visible light, and it is far less affected by dust. Dust grains that block visible light are often transparent to infrared. Several major infrared observatories have studied Stephenson 2-18. The Infrared Astronomical Satellite, IRAS, launched in 1983, was one of the first space-based infrared telescopes. It surveyed the entire sky in infrared, detecting hundreds of thousands of infrared sources, including many cool dusty stars. IRAS data helped flag the Stephenson 2 cluster as a region of interest. The 2-micron all-sky survey, 2MASS, conducted in the late 1990s and early 2000s, mapped the entire sky in near-infrared wavelengths. Two MASS data provided more detailed positions and brightnesses for stars in the cluster, allowing astronomers to start picking out individual members. The Spitzer Space Telescope, launched in 2003, delivered even better infrared images and spectra. Spitzer could observe at longer infrared wavelengths than previous missions, allowing it to see cooler dust and probe deeper into obscured regions. Spitzer observations helped characterize the dust around stars like Stephenson 2 to 18. The Herschel Space Observatory, which operated from 2009 to 2013, observed at even longer wavelengths in the far infrared and sub-millimeter range. Herschel could see the coldest dust and gas, mapping out the material surrounding stars. Ground-based infrared telescopes have also played a major role. The Very Large Telescope in Chile, operated by the European Southern Observatory, has multiple instruments capable of infrared observations. The VLT's enormous mirrors and excellent site location in the Atacama Desert, one of the driest places on Earth, make it ideal for infrared work. The Keck telescopes in Hawaii, two of the largest optical infrared telescopes in the world, have also observed stars in the Stephenson 2 cluster. These telescopes can use adaptive optic systems that compensate for atmospheric turbulence in real time to achieve sharper images. Adaptive optics works by using a deformable mirror that changes shape hundreds of times per second to correct for distortions caused by Earth's atmosphere. This allows ground-based telescopes to achieve image quality close to what space telescopes can manage, at least at infrared wavelengths, where atmospheric distortion is less severe. Spectroscopy is crucial for understanding these stars. By spreading the star's light into a spectrum and analyzing which wavelengths are present, astronomers can determine temperature, composition, velocity, and other properties. High-resolution spectrographs, instruments that produce very detailed spectra, can detect absorption lines from specific elements and molecules. These lines tell us what the star is made of. In the case of Stephenson 2 to 18, spectroscopy reveals the presence of molecules like titanium oxide and water vapor in the star's atmosphere. These molecules can only exist at relatively cool temperatures, confirming the star's status as a cool hypergiant. Spectroscopy can also measure the star's radial velocity, how fast it is moving toward or away from us. This is done by measuring the Doppler shift of spectral lines. If the star is moving toward us, its light is blue shifted. All the wavelengths are slightly shorter than they would be if the star were stationary. If it is moving away, the light is red shifted. The wavelengths are slightly longer. The amount of shift tells us the velocity. For Stephenson 2 to 18, radial velocity measurements help confirm that it is a member of the Stephenson 2 cluster. All the stars in the cluster should share similar radial velocities because they are all moving together through space. Photometry, measuring brightness over time, reveals variability. Automated survey telescopes scan the sky repeatedly, building up light curves that show how a star's brightness changes. For variable stars like Stephenson 2 to 18, these light curves reveal the timescales and amplitudes of variation. Is the star pulsating regularly or irregularly? How much does the brightness shift? These details constrain models of the star's structure and dynamics. Interferometry is a technique that combines light from multiple telescopes to achieve higher resolution than any single telescope could on its own. By precisely measuring the phase of light waves arriving at different telescopes, astronomers can reconstruct images with resolution equivalent to a telescope as large as the distance between the individual telescopes. The Very Large Telescope Interferometer, VLTI, has been used to measure the angular diameters of some nearby red supergiants. These measurements, combined with distance estimates, give direct measurements of physical size. For very distant stars like Stephenson 2 to 18, interferometry is challenging because the angular size is so small, but future interferometer arrays with longer baselines might be able to resolve it directly. That would provide a direct measurement of the star's size, removing much of the uncertainty from current estimates. Now let us explore what happens after a red hypergiant explodes. The supernova will be a Type II supernova, the kind that occurs when a massive star's core collapses. Here is how it works. The star has been fusing progressively heavier elements in its core: hydrogen to helium, helium to carbon and oxygen, carbon to neon and magnesium, and so on. Each stage releases less energy and runs faster than the previous one. Eventually, the core is fusing silicon into iron. This final stage lasts only a few days. Iron is the most stable nucleus. Fusing iron into heavier elements does not release energy. it absorbs energy. So when the core becomes pure iron, fusion shuts down. The core is supported against gravity only by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. But there is a limit to how much mass electron degeneracy pressure can support, called the Chandrasekhar limit. For an iron core, that limit is about 1.4 solar masses. Once the core exceeds that mass, electron degeneracy pressure can no longer hold it up. The core collapses, and it collapses fast. In less than a second, a core the size of Earth collapses to a sphere about 20 miles across. The density skyrockets to nuclear density, around 100 trillion times the density of water. Electrons are forced to combine with protons, forming neutrons and releasing neutrinos. The core becomes a neutron star, an object so dense that a teaspoon of its material would weigh 1 billion tons. The collapse happens so suddenly that the outer layers of the star do not have time to react. They are still falling inward when the core reaches nuclear density and stops collapsing. The infalling material slams into the now solid core and rebounds. This rebound creates a shockwave that propagates outward through the star. The shockwave is enormously energetic. It heats the outer layers to billions of degrees, hot enough to trigger explosive nucleosynthesis. Elements heavier than iron, which cannot be made by normal fusion, are forged in the supernova explosion itself. Gold, platinum, uranium, and other heavy elements are created in this brief moment of extreme conditions. The shockwave blows the outer layers of the star into space at speeds of 10,000 to 30,000 miles per second. This ejected material forms an expanding shell called a supernova remnant. The remnant glows brightly as the shockwave heats the surrounding gas. From Earth, the supernova would appear as a new bright star in the constellation Scutum. It would suddenly appear where no bright star was before, possibly reaching magnitude -7 or -8. That is brighter than Venus. Bright enough to be visible during the day. It would remain bright for weeks, then gradually fade over months. The light curve, the graph of brightness over time, would show an initial rapid rise as the shock wave reaches the surface, a peak as the maximum amount of material is heated, and then a gradual decline as the expanding remnant cools and becomes transparent. The decline would be powered by the decay of radioactive isotopes created in the explosion, particularly nickel-56, which decays to cobalt-56 and then to iron-56. This radioactive decay provides energy that keeps the remnant glowing for months after the initial detonation. The neutrinos released during core collapse carry away most of the explosion's energy, about 99% of it. These neutrinos barely interact with matter and escape almost immediately, streaming out from the core at nearly the speed of light. Only about 1% of the energy goes into the visible explosion, but that 1% is still staggering. A typical Type II supernova releases about 10 to the 46 joules of energy in the form of kinetic energy and light. That is about 100 times the energy the Sun will emit in its entire 10 billion-year lifetime, released in just a few seconds. The explosion would scatter about 10 to 15 solar masses of material into space. This material, enriched with heavy elements created in the star and in the supernova itself, would mix with the interstellar medium. Over millions of years, it would cool and condense, eventually becoming part of new clouds of gas and dust. Those clouds might collapse to form new stars, and those stars would be slightly more metal-rich than Stephenson 2 to 18, continuing the process of chemical enrichment that has been going on since the first stars formed. The core remnant, the neutron star or black hole, would remain behind. If it is a neutron star, it might be detectable as a pulsar, a rapidly rotating neutron star that emits beams of radiation. As the neutron star rotates, these beams sweep across space like lighthouse beams. If one beam happens to point toward Earth, we detect regular pulses of radio waves, hence the name pulsar. Pulsars rotate incredibly fast, some spinning hundreds of times per second. They are incredibly dense, with magnetic fields trillions of times stronger than Earth's. They are some of the most extreme objects in the universe, and studying them teaches us about physics under conditions we can never recreate in laboratories. If the core is too massive for neutron degeneracy pressure to support, it collapses further into a black hole. A stellar mass black hole formed from a star like Stephenson 2 to 18 would have a mass of perhaps 10 to 15 solar masses. Its event horizon would be only about 60 to 90 miles across. Tiny compared to the original star, but containing all the mass of the core. Black holes from stellar collapse are often found in binary systems, orbiting another star. If the companion star is close enough, the black hole can pull material off it, forming an accretion disk. Material in the accretion disk spirals inward, heating up to millions of degrees and emitting X-rays. These X-ray binary systems are some of the brightest X-ray sources in the galaxy. They are easier to detect than isolated black holes because the accreting material glows brightly. Isolated black holes, by definition, do not emit light, so they are very hard to find unless they happen to pass in front of a background star and gravitationally lens its starlight. The supernova remnant would expand outward at thousands of miles per second. Over thousands of years, it would grow to dozens of light-years across. Eventually, it would fade as the material dispersed and cooled. Some famous supernova remnants include the Crab Nebula, the remnant of a supernova observed in 1054 AD. The Crab Nebula is powered by a pulsar at its center, which is spinning 30 times per second and pumping energy into the surrounding nebula. Cassiopeia A is another famous remnant from a supernova that occurred around 1680, although it was not observed at the time because it was heavily obscured by dust. These remnants are laboratories for studying supernova physics, shock waves, and the interaction between ejected material and the interstellar medium. Stephenson 2-18's remnant will one day join this list. It will become another expanding shell of enriched gas, glowing in radio and X-rays, slowly mixing with the galaxy's interstellar medium. One more thing worth discussing is the role of dust around these stars. Red hypergiants are surrounded by thick clouds of dust they have ejected over millions of years. This dust forms when material in the star's outer envelope cools enough for molecules to condense into solid grains. In the hot inner regions close to the star, temperatures are too high for dust to exist. Gas is ionized, atoms are torn apart. But as you move outward, temperatures drop. At a few thousand degrees, molecules can form: water, carbon monoxide, titanium oxide, and others. As you move even farther out, temperatures drop below a few thousand degrees. At those temperatures, solid grains can condense out of the gas. Silicate grains, carbon grains, iron grains, depending on the composition of the gas and the local temperature and pressure. These grains are tiny, typically a fraction of a micron across, much smaller than a grain of sand, but collectively they form thick clouds that can completely obscure the star at visible wavelengths. The dust absorbs visible and ultraviolet light from the star, heats up, and re-emits that energy as infrared radiation. This is why dusty stars are so bright in the infrared. Even if they are faint in visible light, the energy is still there, just shifted to longer wavelengths. Radiation pressure from the star pushes the dust grains outward. Photons from the star strike the dust grains and transfer momentum, creating an outward force. For small grains, this force can overcome gravity, pushing them away from the star. As the dust grains move outward, they drag gas along with them through collisions. This creates a dusty wind, a flow of gas and dust away from the star. The wind carries away mass, gradually stripping the star's outer layers. Over time, the star loses a significant fraction of its mass this way. For Stephenson 2-18, the circumstellar dust shell extends for many stellar radii. It might reach for tens or even hundreds of astronomical units from the star. This dust is what makes the star appear extremely bright in infrared surveys. Instruments like Spitzer and Herschel detected enormous amounts of cool dust around the star, far more than you would expect from a star without significant mass loss. This dust shell is evidence of the star's ongoing mass loss and its approaching end. The more dust there is, the more mass the star has lost, and the closer it probably is to going supernova. When the supernova occurs, the shock wave will plow into this circumstellar material. The collision will heat the material to extremely high temperatures, causing it to glow brightly in X-rays and visible light. This interaction between the supernova ejecta and circumstellar material can last for years or decades after the explosion. It creates a bright expanding shell that is easier to observe than the supernova remnant itself in later stages. Some supernovas show evidence of this interaction in their light curves. The light curve has an initial peak from the explosion itself, then a later bump or plateau as the ejecta collide with circumstellar material. By studying these features, astronomers can learn about the mass loss history of the progenitor star, how much mass it lost and when. Let us also think about the ultimate fate of matter from Stephenson 2 to 18. Right now, the star contains 12 to 16 solar masses of material. Most of that material is hydrogen and helium, the most common elements in the universe. But there is also a significant fraction of heavier elements, carbon, nitrogen, oxygen, and others. These heavy elements were created in earlier generations of stars and were part of the gas cloud Stephenson 2 to 18 originally formed from. Across the star's lifetime, fusion in the core has been creating still more heavy elements: helium to carbon, carbon to oxygen, oxygen to silicon, silicon to iron. The core contains layers of different composition, like an onion. An iron core surrounded by a silicon shell surrounded by an oxygen shell, and so on outward. When the supernova occurs, the explosion will create even more heavy elements through explosive nucleosynthesis. Elements heavier than iron, which cannot be made through normal fusion, get forged in the brief moment of the supernova. All of this enriched material, roughly 10 to 15 solar masses of it, will be scattered into space. It will mix with the interstellar medium, becoming part of the galaxy's reservoir of gas and dust. That gas and dust will eventually collapse to form new stars. Some of those stars will have rocky planets. Planets made of elements forged in stars like Stephenson 2 to 18. And if any of those planets develop life, that life will be made of atoms that were once part of Stephenson 2 to 18. This is the cosmic cycle of matter. Stars create heavy elements, scatter them into space, and new stars and planets form from the enriched material. Across billions of years, the galaxy becomes more and more metal-rich. Each generation of stars is slightly more enriched than the previous one. Earth and the Sun formed about 4.6 billion years ago from a cloud that had already been enriched with heavy elements by previous generations of stars. The iron in Earth's core, the oxygen in our atmosphere, the carbon in our bodies, all of it came from stars that lived and died before the Sun was born. And billions of years from now, after the Sun dies and scatters its outer layers into space, those atoms might become part of future stars and planets, maybe even future life. Matter is recycled endlessly through the cosmos. Stephenson 2 to 18 is part of that cycle, a brief, brilliant phase in the ongoing story of matter's journey through the universe. Before we close, I want to emphasize just how remarkable it is that we can study objects like this at all. Stephenson 2-18 is 19,000 light-years away. That is an almost incomprehensibly vast distance. If you traveled at the speed of a commercial airliner, about 600 miles per hour, it would take roughly 21 billion years to get there. That is longer than the current age of the universe. If you traveled at the speed of the Voyager spacecraft, around 38,000 miles per hour, it would still take about 340 million years. We can never physically visit this star. No spacecraft we can currently imagine could make the journey within a human lifetime, or even within human civilization's lifetime. And yet we can study it in detail. We can measure its size, its temperature, its luminosity, its composition. We can watch it change over time, track its variability, map its structure. We can predict when it will explode and what will happen when it does, all from light that has traveled 19,000 years to reach us. Photons that left the star when humans were still living in small bands, hunting and gathering with no written language, no agriculture, no cities. Those photons have been traveling through space all this time, crossing the galaxy, threading through clouds of gas and dust, finally reaching Earth and entering our telescopes. And from those photons, we can reconstruct the entire life story of a star nearly 2 billion miles across. That is the power of astronomy. That is the power of science. We take tiny clues, faint signals, subtle patterns in light, and from them we build a picture of the universe. We figure out how stars work, how they are born, how they live, how they die. We figure out the laws of physics that govern everything from the smallest atom to the largest galaxy. And we do it all from a small planet orbiting an average star in an unremarkable galaxy. It is one of humanity's greatest achievements. Not building monuments or conquering territories, but understanding. understanding how the universe works, understanding our place in it, understanding where we came from and where we are going. Stephenson 2-18 is a testament to that understanding. A star we will never touch, but can study. A star we will never visit, but can know. A star that exists in a realm of extremes we can barely imagine, and yet we can measure it, analyze it, and comprehend it. Now let us think about some of the practical challenges astronomers face when observing stars like Stephenson 2-18. One major challenge is atmospheric interference. Earth's atmosphere is constantly in motion, with currents of air at different temperatures creating turbulence. This turbulence causes stars to twinkle, which looks beautiful to the naked eye, but is a nightmare for astronomers trying to make precise measurements. The twinkling is caused by light from the star being bent slightly as it passes through pockets of air with different densities. The image dances around, blurs and shimmers. For point sources like distant stars, this creates the twinkling effect. For extended objects like planets or nearby stars that appear as small disks, it creates blur. Adaptive optic systems can compensate for this to some degree. They work by measuring the distortions in real time using a guide star, either a real bright star near the target or an artificial star created by shining a laser into the upper atmosphere. The laser excites sodium atoms about 90 miles up, creating a glowing spot that acts as an artificial star. By measuring how the guide star's light is distorted, the adaptive optic system can figure out what the atmosphere is doing at that exact moment. It then adjusts a deformable mirror in the telescope, changing its shape hundreds or thousands of times per second to cancel out the atmospheric distortions. This dramatically improves image quality, allowing ground-based telescopes to achieve resolution close to their theoretical limit, but adaptive optics only works well at infrared wavelengths. At visible wavelengths, atmospheric turbulence changes too quickly for the system to keep up perfectly. So even with adaptive optics, ground-based observations have limitations. Space-based telescopes do not have this problem because they are above the atmosphere. The Hubble Space Telescope, for instance, can observe at visible wavelengths with no atmospheric interference. But Hubble is optimized for visible and ultraviolet light, not infrared. For infrared observations, you need specialized instruments. The James Webb Space Telescope, launched in December 2021, is a powerful infrared observatory. It has a much larger mirror than Hubble and is optimized for infrared wavelengths. Webb can observe very faint, very cool objects that are invisible to Hubble. It is likely that Webb will eventually observe Stephenson 2-18 and other red hypergiants in unprecedented detail. Its high-resolution infrared imaging might allow direct measurement of the star's angular size, which combined with distance estimates would give a precise physical radius. Webb spectrographs could analyze the star's atmospheric composition in detail, identifying specific molecules and isotopes. This would provide clues about the star's evolutionary history and internal processes. Another challenge is distance measurement. Knowing how far away a star is crucial for determining its physical properties. Brightness alone does not tell you much, because a faint nearby star and a bright distant star can appear equally bright from Earth. You need distance to convert apparent brightness into actual luminosity. For nearby stars within a few thousand light-years, astronomers use parallax. As Earth orbits the Sun, nearby stars appear to shift positions slightly against the background of more distant stars. By measuring this shift, you can triangulate the distance using basic geometry, but parallax only works for relatively nearby stars. Beyond a few thousand light-years, the shift becomes too small to measure accurately, even with space telescopes like Gaia, which has measured parallax for over 1 billion stars. For more distant stars, astronomers use other methods. If the star is part of a cluster, you can estimate the cluster's distance using various techniques, then assume all stars in the cluster sit at roughly the same distance. For Stephenson 2, astronomers have used several approaches. One is spectroscopic parallax, which uses the star's spectrum to estimate its luminosity class, then compares apparent brightness to inferred actual luminosity. Another is kinematic distance, which uses the star's radial velocity and proper motion, its motion across the sky, to estimate distance based on models of galactic rotation. A third method involves studying the cluster as a whole. If you can identify enough cluster members and measure their properties, You can use statistical methods to estimate the cluster's distance. All these methods carry uncertainties, which is why distance estimates for Stephenson 2 range from about 17,000 to 20,000 light-years. The uncertainty in distance propagates into uncertainty in the star's physical properties. If the distance turns out to be 18,000 light-years instead of 19,000, the star's luminosity would be different, which would affect the inferred radius. This is why radius estimates for Stephenson 2 to 18 come as a range rather than a single precise number. Improved distance measurements would shrink that uncertainty. Let us explore what we can learn from the star's variability. As mentioned earlier, Stephenson 2 to 18 is variable. Its brightness changes over time. These variations provide a window into the star's internal structure and dynamics. The two main causes of variability in red hypergiants are pulsations and surface convection. Pulsations are rhythmic expansions and contractions of the star. The entire star swells up, then shrinks back down, then swells again. This happens because there is a feedback mechanism in the star's outer layers. When the star compresses slightly, the material becomes denser and hotter. Hot material is more opaque. It absorbs more radiation. The absorbed radiation heats the material further, causing it to expand. As it expands, it cools and becomes less opaque. Less opacity means less heating. So the material stops expanding and begins contracting again under gravity. This sets up an oscillation, like a spring being compressed and released. The period of oscillation depends on the star's size and mass. Bigger stars have longer periods because it takes longer for pressure waves to travel through them. For a star like Stephenson 2 to 18, the pulsation period might be anywhere from hundreds to thousands of days. By measuring the period and amplitude of pulsation, astronomers can constrain the star's mass and internal structure. Different models predict different pulsation behaviors, so observations can test and refine those models. Convection is the other major source of variability. Inside a star, energy is transported from the core to the surface by either radiation or convection. In some regions, radiation is more efficient. Photons diffuse outward, scattering off atoms and gradually carrying energy away. In other regions, convection is more efficient. Hot material rises, cool material sinks, creating circulation currents that transport energy. In red hypergiants, the outer envelope is highly convective. Giant cells of rising hot gas and sinking cool gas cover the star's surface. Each cell might be larger than Earth's entire orbit around the Sun. As these cells evolve and shift, the star's surface becomes patchy. Some regions are hotter and brighter, others are cooler and dimmer. As the star rotates, these patches move in and out of view, causing brightness variations. If we could somehow get a close-up image of Stephenson 2 to 18, we would not see a smooth, uniform surface. We would see a mottled, boiling surface with huge bright and dark patches constantly shifting and evolving. It would look more like the surface of boiling water than the smooth surface of the Sun. Observing these variations across months and years builds up a picture of the star's surface dynamics. How quickly do the convection cells evolve? How large are they? How much do they affect the overall brightness? These details help astronomers understand convection at scales and conditions that can never be replicated in laboratories. The Sun also has convection cells, called granulation, but they are much smaller, only about 600 miles across. Stephenson 2-18's convection cells are hundreds of millions of times larger. Understanding convection in extreme stars helps refine our broader understanding of convection, which is important because convection plays a role in many astrophysical contexts, from planetary atmospheres to neutron stars. Now let us talk about the role of rotation. Stars rotate, some faster than others. The Sun rotates once every 25 days at its equator, slower at higher latitudes, because the Sun is a gas and different latitudes can rotate at different speeds. Massive stars on the main sequence often rotate much faster, some completing a rotation in just a few hours. This rapid rotation affects their structure, creating an equatorial bulge and influencing their evolution. Red hypergiants, by contrast, rotate very slowly. As a star evolves off the main sequence and expands, conservation of angular momentum should make it spin faster, like a figure skater pulling in their arms. But the opposite happens. Red giants and hypergiants rotate slower than their main sequence progenitors. This is because they are losing mass through stellar winds, and that mass carries angular momentum away with it. As the star sheds its outer layers, it loses not just mass but also rotational energy. The result is a slowly rotating bloated star. Stephenson 2-18 probably rotates once every several years, maybe even longer. This slow rotation has consequences. It means the star is nearly spherical, with little or no equatorial bulge. It also means rotation does not significantly affect the star's structure or evolution at this stage. Contrast this with massive stars on the main sequence, where rotation can be a major factor. Rapid rotation can mix material between the core and envelope, bringing fresh fuel to the core and extending the star's lifetime. It can also create strong magnetic fields and drive stellar winds. But for Stephenson 2-18, rotation is a minor effect. The star's evolution is dominated by nuclear fusion, mass loss, and radiation pressure, not rotation. This simplifies the modeling somewhat, because rotation adds complexity to stellar models. For slowly rotating stars, you can treat them as spherically symmetric, which makes the mathematics much easier. Let us think about the broader context of massive star evolution. Stephenson 2-18 did not start out as a hypergiant. It was born as a massive main sequence star, probably a hot blue star, tens of times more massive than the Sun. It spent a few million years on the main sequence, fusing hydrogen into helium in its core. During this time, it was incredibly luminous, perhaps 100,000 times more luminous than the Sun, and incredibly hot, with a surface temperature of 30,000 Kelvin or more. It was a blue supergiant, not a red hypergiant. But as it exhausted the hydrogen in its core, it began to evolve. The core, now mostly helium, contracted and heated up. This contraction released gravitational energy which heated the surrounding hydrogen shell. The hydrogen shell began fusing, creating a new energy source. The outer envelope, responding to this new energy source, expanded. As it expanded, it cooled, and the star transitioned from blue to yellow to red. It became a red supergiant. But the evolution did not stop there. As the core continued to contract and heat up, helium fusion ignited in the core. This created even more energy, causing the envelope to expand even further. The star grew larger and cooler, eventually becoming a red hypergiant. At some point, probably in the near future on cosmic timescales, the star will exhaust its nuclear fuel. It might undergo a final phase of instability, perhaps pulsating violently or ejecting large amounts of mass in eruptions. Some red hypergiants show evidence of episodic mass loss, brief periods where they eject huge quantities of material in eruptions lasting months or years. These eruptions might be triggered by instabilities in the envelope, or by the ignition of new fusion shells in the core. Eventually, the core will collapse, and the star will explode as a supernova. This entire evolutionary sequence, from main sequence star to supernova, takes only about 20 million years. That is incredibly fast by stellar standards. Compare it to the Sun, which will spend about 10 billion years on the main sequence before evolving. Massive stars live fast and die young, but their impact on the galaxy is enormous. Their powerful stellar winds and eventual supernova explosions enrich the interstellar medium with heavy elements. They create new stars by compressing nearby gas clouds with their shock waves. They can even trigger the formation of new stars by their radiation pressure and winds. Many star-forming regions show evidence of triggered star formation, where the shock wave from a supernova or the radiation from massive stars compresses nearby gas, causing it to collapse and form new stars. So Stephenson 2-18, despite its short life, plays a crucial role in the galaxy's ecology. It is part of a cycle of star formation, element creation, and renewal that has been running for billions of years and will continue for billions more. Another aspect worth discussing is the comparison between different types of hypergiant stars. Not all hypergiants are red. There are also yellow hypergiants and blue hypergiants, although they are even rarer than red hypergiants. Yellow hypergiants are believed to occupy a very brief transitional phase. They are stars that are either expanding from blue supergiant to red supergiant or contracting from red supergiant back to blue supergiant. This phase might last only a few thousand years, incredibly brief even by stellar standards. Because it is so brief, there are very few yellow hypergiants known. Rho Cassiopeia is one example, a star that has shown dramatic variability and mass loss episodes. In 1998, it dimmed by about 1 magnitude over a few months, apparently due to ejecting a large cloud of dust. Yellow hypergiants are unstable, sitting in a region of the Hertzsprung-Russell diagram called the yellow evolutionary void. This void exists because stars evolve through this region so quickly that they are rarely observed there. Blue hypergiants sit at the other extreme. Incredibly hot and luminous stars with surface temperatures of 20,000 to 50,000 Kelvin. They are among the most luminous stars in the universe, outshining even red hypergiants, but they are also rarer and less well understood. Examples include Rigel and Orion, which is sometimes classified as a blue supergiant or a blue hypergiant depending on the criteria used. P Cygni is another famous blue hypergiant known for its strong stellar wind and distinctive spectral features. The star shows evidence of substantial mass loss, with shells of previously ejected material surrounding it. Blue hypergiants are believed to be evolving rapidly, possibly undergoing dramatic changes over timescales of centuries or millennia. They might represent stars that are about to explode as supernovae, or stars that are transitioning to a different evolutionary phase. The exact evolutionary relationships between blue, yellow, and red hypergiants are still being worked out. Do all massive stars pass through each phase, or do some skip certain phases? Does a blue hypergiant always become a red hypergiant, or can it explode as a supernova while still blue? These are active areas of research. Observations of hypergiants in nearby galaxies, particularly the large and small Magellanic Clouds, have helped clarify some of these questions. The Magellanic Clouds are small satellite galaxies of the Milky Way, close enough that individual stars can be studied, but far enough away that they offer a different perspective. Different metallicity, different star formation histories, different environments. Studying hypergiants in these galaxies and comparing them to Milky Way hypergiants helps astronomers understand how metallicity and environment affects stellar evolution. One key finding is that metal-poor stars, those with fewer heavy elements, tend to retain more mass and explode at higher masses. Metal-rich stars like those in the Milky Way lose more mass through stellar winds and explode at lower masses. This affects the type of supernova they produce and the remnant they leave behind. Metal-poor stars are more likely to leave behind black holes. Metal-rich stars are more likely to leave behind neutron stars. Stephenson 2 to 18 being in the Milky Way has roughly solar metallicity, or perhaps slightly higher. Its evolution and fate will be shaped by that metallicity. Let us also discuss the philosophical implications of studying stars like Stephenson 2 to 18. Astronomy has always carried a philosophical dimension. Looking up at the stars compels us to think about our place in the universe, about scale, about time, about existence itself. Stephenson 2 to 18 embodies some of these big philosophical questions. First, there's the question of scale. Humans evolved to grasp scales relevant to survival. Distances of meters to kilometers, timescales of seconds to years. We are not built to intuitively comprehend billions of miles or millions of years. And yet, through science, we can extend our understanding far beyond our intuitive limits. We can comprehend objects billions of times larger than anything in our direct experience. This is one of the triumphs of human cognition. We are not bound by our senses or our intuition. We can build instruments to extend our senses, telescopes to see farther, spectrographs to analyze light in ways our eyes simply cannot. We can build mathematical models to represent things we cannot directly perceive. And through this process, we gain understanding of phenomena far removed from everyday life. Second, there is the question of impermanence. Stephenson 2 to 18 is a reminder that nothing lasts forever. Stars are born, they live, they die. Even the largest, most impressive stars have finite lifetimes. And on cosmic timescales, those lifetimes are brief. 20 million years feels like a long time to us. It is far longer than human civilization has existed, longer than our species has existed. But within the context of the universe's 13.8 billion-year history, it is a blink. The star will live and die in less than 1/5 of 1% of the universe's current age. It is a fleeting phenomenon. This impermanence extends to everything. Planets, galaxies, even the universe itself will eventually change beyond recognition. In trillions of years, all the stars will burn out. All the galaxies will drift apart, and the universe will be a cold, dark, empty place. Nothing we can see today will remain. Some people find this depressing, but others find it liberating. If everything is temporary, then the present moment gains significance. The fact that we exist now, that we can observe the universe in its current state, is remarkable. We are privileged to live in an era when stars still shine, when galaxies are still forming, when the universe is still dynamic and interesting. Third, there is the question of connection. Stephenson 2-18 sits 19,000 light-years away. We will never visit it. No human ever will, unless some radical new physics is discovered that allows faster-than-light travel. And yet we are connected to it. The atoms in our bodies were created in stars like it. The oxygen we breathe, the carbon in our DNA, the iron in our blood, all of it came from massive stars that exploded billions of years ago. We are literally made of stardust, not as a metaphor, but as a literal fact. And when Stephenson 2-18 explodes, it will scatter its enriched material into space. That material will eventually become part of new stars, new planets, maybe even new life. There is a cosmic recycling at work, a connection that spans space and time, linking all matter in the universe into a grand cycle. We are part of that cycle. We are not separate observers looking at the universe from outside. We are inside it, made of it, shaped by it. This perspective, sometimes called the cosmic perspective, can be humbling and empowering at the same time. Humbling because it shows how small we are, how brief our existence is on cosmic scales. Empowering because it shows that we are part of something much larger than ourselves. Part of a universe that has been evolving for billions of years and will continue evolving for billions more. Our lives have meaning, not in spite of our smallness, but because we are part of this larger story. Now let us think about the future of red hypergiant research. What will astronomers learn in the coming years and decades? Several new instruments and missions will revolutionize our understanding of these stars. The James Webb Space Telescope, as already mentioned, is operational and will provide unprecedented infrared observations. Webb's high-resolution imaging could potentially resolve the surfaces of nearby red supergiants, revealing individual convection cells directly. For more distant stars like Stephenson 2-18, Webb will provide detailed spectra revealing atmospheric composition, temperature structure, and variability. The extremely large telescope, currently under construction in Chile, will have a mere 39 meters in diameter, making it the largest optical telescope ever built. With adaptive optics, it will achieve resolution far exceeding current telescopes. It might be able to directly measure the angular size of Stephenson 2-18, providing a precise radius measurement. The Square Kilometre Array, a radio telescope being built in Australia and South Africa, will be sensitive enough to detect faint radio emission from stellar winds and circumstellar material around hypergiants. This will help map the mass loss rates and wind structures in detail. Future X-ray missions will study the high-energy emission from hypergiants, revealing information about magnetic fields and shock waves in stellar winds. These observations will come from missions like Athena, the advanced telescope for high-energy astrophysics, planned for launch in the 2030s. Gravitational wave observatories, while primarily designed to detect black hole and neutron star mergers, might also detect signals from supernova explosions. If Stephenson 2-18 explodes as a supernova, next-generation gravitational wave detectors could potentially detect the gravitational waves from the core collapse. This would provide a completely new way to study supernova, seeing directly into the collapsing core rather than just observing the light from the expanding envelope. Computer simulations are also improving rapidly. Modern supercomputers can simulate stellar evolution with unprecedented detail, tracking nuclear reactions, energy transport, and mass loss in 3 dimensions. These simulations are revealing new insights into how convection works in hypergiant envelopes, how pulsations develop and propagate, and what triggers the final collapse. By comparing simulations to observations, astronomers can test and refine their models, gradually building a more complete understanding of these extreme stars. Let us close with a thought about perspective. When you look up at the night sky, you are seeing mostly main sequence stars, ordinary stars like the Sun burning hydrogen steadily. The hypergiants are out there too, but they are rare, and many are too distant or too obscured to see with the naked eye. Stephenson 2-18 is invisible to the unaided eye, hidden behind dust and distance. But just because you cannot see something does not mean it is not there. The universe is full of wonders that are invisible to our eyes but visible to our instruments and understandable through science. Stephenson 2-18 exists right now, 19,000 light-years away, a glowing ember larger than anything in our direct experience. It is shining, pulsating, losing mass, approaching the end of its life. In a few million years, maybe less, it will explode. The light from that explosion will travel through space for 19,000 years. It will arrive at Earth in our distant future, long after everyone alive today is gone. Maybe humans will still exist. Maybe they will have telescopes to observe the supernova. Maybe they will remember that their distant ancestors studied this star, predicted its fate, understood its nature. Or maybe humanity will be gone, and the supernova will blaze unseen, except perhaps by other intelligent species elsewhere in the galaxy. Either way, the explosion will happen. The laws of physics do not care whether anyone is watching. The star will complete its life cycle, scattering enriched material into space, contributing to the ongoing evolution of the galaxy. And that material will eventually become part of new stars, new planets, maybe new life. The cycle continues. For now, we can study Stephenson 2-18 from afar. We can measure it, analyze it, understand it. We can appreciate its extreme scale, its brief life, its crucial role in the cosmic ecology. And we can marvel at the fact that we, tiny creatures on a small planet, can comprehend something so vast and so distant. That is the power of the human mind. That is the gift of science. That is what makes us uniquely capable of understanding the universe we find ourselves in. Stephenson 2-18, the largest star ever observed, stands as a testament to the universe's capacity for extremes. It is a star that pushes the limits of size, luminosity, and instability. It is a star that challenges our models and expands our understanding. It is a star that reminds us of the vastness and diversity of the cosmos. And it is a star that connects us to the larger story of matter's journey through space and time. Thanks for joining me on this exploration of the largest star in the universe here on Hidden Beyond Stars. If you found this journey as fascinating as I did, consider liking the video and subscribing to the channel. It helps these stories reach more people who share our curiosity about the cosmos. And remember, the next time you look up at the night sky, somewhere out there in the constellation Scuti, invisible to your eyes but real nonetheless, Stephenson 2-18 is shining. A cosmic giant living fast, burning bright, and preparing for its final magnificent farewell.